Hello, everyone. Welcome to today's journal club of the MICCAI RISE. And it's a pleasure for me to invite Dr. Julia Wolleb. She's postdoc fellowship at the Yale University. She completed her PhD at the University of Basel, where I had the opportunity to collaborate with her. And her works are extremely recognizable in the MICCAI community and the medical field. Even she got the global impact work in 2024 for her work in the diffusion models for medical anomaly detection. And today she's going to talk about the worst generalizable neural representations for medical images and video. So let's learn a lot from her. And thank you very much, Julia. The stage is yours.
Thank you. Thanks for having me. It's really nice that I can present here. As Alvaro already said, at the moment I'm a postdoc at Yale, and I work on neural representations of images, and that's what I'd like to talk about today. As a short background, or like the clinical motivation behind the project, is that initially I joined a global health lab, and there we were working on point-of-care ultrasound, especially for emergency medicine and also in low-income settings. And here on the left, you see an image of our collaborators in South Africa, where they run clinical trials for lung ultrasound. And for this, they use point-of-care ultrasound. And the definition, or like the characteristics of point-of-care ultrasound, is that they use a portable device. You can see this here. The doctor is handing a device in the size of a hand that she can carry everywhere in the hospital where she needs it. The second thing is that it is used at the patient's bedside, so you can do this in emergency care very quickly because you don't need to move the patient somewhere else. And it's used for real-time assessment. And you can see this on the tablet, so you can just plug the probe into a tablet and you can see what you're scanning at the moment. And all of this together is very useful, as I said, in emergency settings when you need to be quick with your assessment, so there's a sense of urgency. And also it's nice for children because it's non-invasive. And in low research settings, it's valuable because it's so cheap. And sometimes we don't have access to more advanced or more expensive imaging technologies. And there the question is more like, when is ultrasound good enough compared to the more expensive modalities, or how far can we get using ultrasound compared to X-ray or CT or whatever? In this case, there are two clinical trials. So one is for tuberculosis in adults, and the other one is for pneumonia in children. So these are more like lung focused. But other than that, in emergency care, you can use ultrasound for a lot of things from head to toe. But of course, you can't go through the bone. Like classic applications would be, for example, cardiac ultrasound, where you look at the heart. And this is extremely helpful when someone may have heart failure. And also, if someone may have heart failure, you can also look at the lungs in addition to check whether it's maybe a lung problem or a heart problem. Then you can use it for anything abdominal because there's a lot of soft tissue and not too much bone involved. And of course, when someone is pregnant, that's kind of like a very useful tool, as all of you know probably. So overall, ultrasound is used every day in the clinics. However, it's also a little bit tricky because here on the left, you see 6 different lung ultrasound videos. And so it's the same imaging modality on the same organ, but still all the videos look so different to each other, and this makes it really challenging. So because we can have a lot of different acquisition settings, all these videos are difficult to interpret and to get to a diagnostics in the end. And also one issue is that the acquisitions really depend on the operator, so on the doctor using the device. And actually, they also don't like to read each other's videos because they say it's like reading another person's handwriting, and everyone does it a little bit differently. And this introduces a huge bias into the data set. And one other thing is that even if you have like the perfect acquisition settings, if the patients move, and especially this is difficult for children or for babies. When they cry and they move, it's really hard to acquire high quality ultrasound videos. And if you have lower quality videos, the downstream interpretation gets hard. And nevertheless, so there's a lot of challenges, but still we try to figure out whether we can use AI to support the interpretation of all these videos. And here the emphasis is really on the interpretation once the videos are acquired. There is a separate line of research that does AI-guided acquisition when you use AI to actually acquire the videos, but that's not what we do here. So given all these challenges, the objectives of my postdoc projects here are to develop a deep learning model that can analyze the ultrasound videos. And here it's really a focus on the videos rather than still frames. A lot of previous work, they picked the videos and they picked one frame out of the video, or an expert selected this frame, and then you have basically a still image rather than the full video. However, when you then talk to the clinicians in the hospital, what they actually look at is the changes from frame to frame, like how does the lung move, how does the heart move. So the information, or a lot of information, is in the movement rather than in a static frame. And that's why in this project we focus on the full videos rather than an expert selected frame. And the last part is the very tricky part, like can we get models that are robust across this great variability of data that we collect when we acquire ultrasound videos. And to tackle all of these three objectives, I started with classic video architecture. So I used time-resolved convolutional neural networks that are also used for other video analysis tasks for like real, like natural videos. And to make them more robust towards this great variability of data, I first tried some filtering and clustering algorithms. And the goal is always in this setting to get a triage score. It's kind of like, how bad is this patient? How urgently do I need to treat this patient? And so from the video, I try to predict a disease severity score. So it's kind of like a classification task. And so this is one way to do this. However, I then tried another way, which is, can I take the video and learn a useful data compression such that a video, which is a sequence of frames, so it's a sequence of images, can I compress it into a series of 1D vectors and then apply a way smaller model to the series of 1D vectors to get to the same disease severity score? And today I'm going to talk about this lower path, and this is very exploratory. So I was just like curious, can I also use this alternative architecture to solve this classification task? And this is all work in progress, so it's far from being done, but I still thought it would be nice to share and like show you what we do at the moment. So this learnable data compression, I do it based on implicit neural representations. So first we need to understand how they work. And in their classic formulation, they look like this. So right now we talk about images. So we leave out the time component for the moment, and I'll come back to the time-resolved analysis later on. So here I just talk about the still frame. So let's say I have one frame of my video, and this is my input image, and I can pick any coordinate x, y of this image. So here I mark it with a red cross. So this red cross is at the location x and y. And I feed x and y through a multi-layer perceptron. And this MLP predicts the grayscale value at this location. And so I train this MLP specifically for this image. So I overfit the MLP for my image. And once I train it, I can then sample all coordinates I'd like from my like input image and predict the grayscale value at this location. And in this way, I can reconstruct my image. I also can sample in between coordinates, so that's nice for super resolution. But that's also like a different line of research. And once I have trained my MLP on my image, I can basically forget about my input image and just keep my MLP, because this MLP stores all the information I need. So I represent my input image in the form of an MLP, and so this is my neural data representation. So this has been presented in 2020, so a while ago, and it works quite well. However, there is one downside. So when we have a large data set, so let's assume we have a data set of X-ray images, and let's say we have 10,000. In the original formulation, we would need to fit one MLP per image. And this would be very expensive, and it would take a lot of time. And therefore is very inefficient. So now the idea is that in my image data set, I know that all my X-ray images, they kind of look similar. So they all have two lungs, they all have ribs, they all have a spine, they all have shoulders. And now the idea is, okay, I learned this general representation once, and then I only need to fine-tune to my specific patients. And that's the idea of this paper called MedFuncta that is now submitted and under review. So we have this image data set that contains a lot of images, but they are similar to each other in a way. And we define an MLP, just like in the formulation that we had before, that is in the blue block, that learns a shared representation over the whole data set. But then for like a specific image one, I define a signal-specific parameter phi1 that I use to condition my shared MLP in the blue block to represent my specific image. So for my image one, I will have a neural representation based on the shared network parameters theta and phi1. For my second image, I would have the same shared network parameters theta, but signal-specific parameters phi2, and so on and so forth. And I have as many signal-specific parameters as I have images in my data set. And once I train all of this, I will store my whole image data set as a set of 1D vectors. So all of these green vectors are 1D vectors. And then I can apply my downstream tasks on these vectors phi rather than the image space. And that's basically the whole idea in a nutshell. Now the question is, so how does this network look like, and how do we train such a thing? And as I said, the blue block still is a multi-layer perceptron, so we don't change anything about the architecture. One thing to note is that the activation functions are sign activation functions. There's also alternatives to that, but yeah, there are papers who took other activation functions, but here we stick to the sign. So my blue block consists of multiple layers, multiple linear layers. And the input is still my coordinate xy, and I try to predict the pixel intensity at this coordinate xy. Now, as I said, we need to condition my shared block, the shared blue block, with a signal-specific parameter phi for my specific image. And I do this with this green 1D vector that is passed through a linear layer here. This modulation is just a linear operation. And then it's added to the output of the linear layer for each layer. So it's a shift modulation. I take the output of my linear layer and I add the shift modulation given by this green vector. And I do this in every layer. And the way I train this is I just apply a mean square error loss between the predicted grayscale value and the true grayscale value at this coordinate. Then with this, what I actually want is that I start with a random initialization of the blue block theta, and I try to walk to an optimal shared representation theta star. And once I have like a good representation theta star that kind of like shows how the data set in general looks like, I just have a short walk to my image-specific representation, phi1, phi2, or phi3, and so on and so forth. Now, during training, we need to apply a couple of tricks because it's quite expensive and we need to fit everything into a GPU. So in the training loop, we initialize phi0 as 0. So we always start with phi as equals to 0. And then we do chi inner loop update steps. So we first optimize the green part. So we go from phi0 to phi1 and so on to phi chi. Usually this is like 10 or 20, so not a lot really. And because here we need to start the second order gradients, we need to reduce the context set. So here the C reduced means that we don't sample all coordinates from my image, we just sample a random subset of coordinates of my image to make this whole thing cheaper. So usually we only sample like 10 or 20% of the coordinates to train my green vectors phi. And once I did 10 steps here, I do one meta update to update theta, so to update the shared parameter. So it's kind of like first the inner loop, then one meta update, then you load the next image, you do 10 inner loop steps and one meta update step. So you train this until your images look good in the reconstruction, and then during inference, so at test time, what we do is we freeze the shared weights theta star because we assume that we learned something useful. And then at test time, we don't need to store the second order gradient, so we can use the full context set, so we can sample all coordinates to update the signal specific parameters phi for 10 or 20 steps. And so maybe one thing to really highlight here is that in this scenario, during test time, I get a new image and I still optimize my signal-specific parameters phi to represent my image. So at test time, I optimize the green part, but not the blue part. And then when I do this on different medical data sets, like the reconstruction performance actually is quite good. The authors tried it on 1D, 2D, and 3D signals, with the only difference there being whether you feed X, XY, or XYZ to your model. And we also tried a lot of different input modalities like X-ray, OCT, histopathology, MRI, and so on and so forth. But here, what I'd like to say is that these images are quite tiny. So they're like 64 by 64. So it's still kind of like a dummy test. It's not really a high resolution approach. However, then in a second set of experiments that you can see here at the bottom right, we tried to scale it up to 128 by 128 and 224 by 224, and it still worked. So it's just kind of like this first set of experiments shows that the reconstruction works well, and we can potentially also scale it up to larger 2D images. What we haven't done yet is testing it on large 3D volumes, which might be tricky in terms of GPU consumption. So these are the reconstruction results. And as I said in the beginning, what we're also interested is in some downstream classification task, for example. So when we remember this whole framework, so we have a shared representation in blue, and then we have as many signal-specific parameters as we have images in our data set. We apply the downstream tasks on these 1D vectors phi. And here you see the classification results on two different data sets. So it's a chest X-ray where we just have two classes, and on the dermatoscope data set where we have 7 different classes. And we see that an MLP on phi actually is better or like performs similarly to a ResNet or an efficient net architecture on the images directly. So this is really nice to see that actually we can just use a very small MLP that is way faster and way cheaper to train on 1D vectors rather than an image architecture. However, as I said, at the moment, these are like super small images, and maybe we need to test all of this on more advanced downstream tasks. So that's kind of the basic MET-functa architecture that was designed for still images. But as I said in the beginning, when we look at ultrasound, what we are interested in is the full video, so a time-resolved representation. So it's like image after image after image after image. And for this, we need to change the architecture a little bit. And that's my work that I presented in the ultrasound workshop at MICCAI a couple of weeks ago. So the idea is I have an input video V that consists of frames that have coordinates x, y, but I also have this time dimension t. And now the idea is, first of all, we have redundant information that is shared across the data set that is stored in this blue block. So this is the same blue block as we had before. But then in addition to that, now we also have redundant information over time. So we have information that is shared from frame to frame. For example, what is the depth? What is the contrast? How much noise roughly do I have? What organ do I look at? How wide is the beam? So this is all information that is kind of like consistent over the frames. And I want to store all of that in a video-specific representation vector V. But then on top of that, so this is kind of like a hierarchical approach. In the finest level, I want to store information that changes from frame to frame. So what is different from frame 1 to frame 2 to frame 3? And this is stored in this time-resolved representation phi1 through phi t. So per frame, I have one frame-specific vector phi t. But still, the reconstruction task stays the same. So for every coordinate, I try to predict the grayscale value at this coordinate. And then the downstream task, in my case, also is then applied to this video-specific and the time-resolved representations phi and v. The motivation or my idea why I try to do it like this was that I hope that all the bias that I actually don't want will be stored in V. For example, the operator or the probe that I use, and that the changes from frame to frame, for example, how does the heart beat, will only be stored in phi. So I was hoping to get some sort of disentanglement in this representation space, but that's stuff that I still work on, so I'm not there yet. Regarding the network architecture, this is also very similar to what we had before. So the blue block is still my MLP with shared parameters theta. So in every layer, I have a linear layer of my MLP followed by a sign activation. But now instead of one modulation vector, I have two. So in every layer, I add the shift modulation of my frame phi k, for example, if you look at the k frame, as well as the shift modulation coming from my video-specific modulation V here. So in every layer, I add two modulations before going through the sign activation functions. And I do this for every layer to predict z hat, which is the grayscale value at my coordinate xy. So that's the architecture. And now for the model training, I again do the same loops as we had before. So I pick a coordinate xy of my frame, I pass it through my MLP, and I compute the mean square error between the true and the predicted grayscale value. And I do the loops again. So first I update V and phi at the same time for 10 inner loop steps. And then once I do this, I update the blue block for one meta update step, and then I load the next image. And so here, when I do the 10 inner loop steps, I really don't touch phi and v. I just let the model do whatever it wants. This will be also follow-up work to kind of like give more structure or restrictions in this representation space. Then, so that's during training. During inference, I load a frame that the model has never seen before. I freeze my blue block and I update my video-specific representation, the time-resolved representation for 10 inner loop steps. So with only very few steps, I can find a neural representation of a video that the model has never seen before. Then during inference, there's one thing, especially if the videos are long, I run into GPU issues. And that's why so it's kind of a hack, but it's a sort of autoregressive approach. So I have an input video that is capital T frames long, and I divide it into batches. So I select the first batch of B frames, where B is just as many frames as I can fit into my GPU. So let's say I load my first 10 frames, and I update V and my V1 through V10. And I keep the blue block frozen. And then the assumption, it's not optimal, but the assumption is that, okay, now my video specific representation should know what organ I look at, for example, or how wide the beam is. So in all subsequent batches of frames, I freeze V, and the only thing I update are the V, which are the changes from frame to frame. And like this, I can just like walk through my whole video until I have no more frames left. And yeah, that's it. I tried this approach on different data sets. So the first one would be a lung data set that was collected at Harvard Medical School. And here the task is B-line detection. B-lines are like comet tails artifacts that kind of like go down in the ultrasound. And you see it here a little bit. So it would be these bright lines here are B-lines. And they are actually signs of liquid on the lung that should not be there. And I have a set of roughly 2,000 lung ultrasound videos. Then the second one is actually not point of care, but it's a very large database of cardiac videos. So I have like roughly 10,000 cardiac videos from this Econet dynamic data set. And here the downstream task is ejection fraction. It's basically how well does the left ventricle pump. And then the last data set is quite a small one. So I got 188 breast ultrasound videos. And here the downstream task is a classification task between benign and malignant lesions. And here I added this data set because first of all, it's smaller. And also you can see it's like it's acquired with a linear probe. So you don't have the beam, you have the full image. So I just wanted to see how my reconstruction task also works on this type of videos. And so I trained my method on all of these data sets first separately. So I trained one model for heart, one model for lung, and one model for breast. And these are the results. So on the top row, you see the input videos of my test set. And in the bottom row, you see my reconstructed videos. And this is at the compression rate of roughly 25. So I do compress the input videos into these 1D modulation vectors, and there's the compression rate of roughly 25, and from there I reconstruct the full videos. What you see is that I do lose noise, so I struggle reconstructing high frequency detail. However, on this data set, I'm not that much interested in noise because what I'm interested in is like how does the ventricle wall behave and how well do the valves open and close and stuff like that. So that worked quite well actually. Then on the lung data set was a little bit more tricky for the reason that on lung ultrasound we are interested in very fine details. Sometimes the B lines are so fine, and also the movement of the pleural line is very like fine-grained. And if I can't reconstruct high-frequency components well, I lose information. But still, we see that the main characteristics are very well preserved. And the same actually holds for at the breast ultrasound. We do lose some high-frequency details, but like the overall video looks the way it's supposed to look like. And then one note from the last time I gave this presentation, it was like, okay, what's the contribution of V? What's the contribution of V in these reconstructions? So here you see on the top row is the input and the bottom row is my reconstruction. And I just plot different frames. And on the very last one, so this image here is when I set all the V's to 0 and I only reconstruct using V, so this yellow part here. So you see that V definitely stores like the beam width, and it also kind of like stores where the ventricle will be. But then the like fine details that change from frame to frame can only be seen if I add phi on top. So here we have phi1, phi5, phi9, phi13, and so on and so forth. So both in combination can reconstruct all the frames well. And V separately is this image here that kind of like gives me like sort of a mean frame over this video, which was actually pretty nice to see. So, and all of these results were if I train one model per data set, which most people usually do. And then what I try to do is what happens if I put all my data sets in together. So I create one huge mixed data set that contains heart, lung, and breast. And I train one model for all three of them. And these are the results. And you can see we do lose some performance, but it's also not terribly, terribly bad. So we can still definitely see the heart pump. We can still see that it's supposed to be a long ultrasound video. And on the breast also, like, as I said before, the high frequency components are maybe even a little bit worse, but still not completely off. Then what we can do with this is like, okay, I have now all three organs in one data set. And here in this t-SNE plot, I showed the video-specific representations V, so just the yellow parts for all three data sets. And here we see that they really cluster well. So we have one cluster for the heart, one cluster for the lung, and one cluster for the breast, which means that V actually stores anatomic specific information, and that's what we wanted. Regarding the reconstruction scores, what we see, so first of all, in this blue block, we compared to the 2D baseline where we just reconstruct every frame separately. So this would be the MedFuncted 2D. We also tried the 3D version of it where we treat the video as a 3D volume, but here I had to cheat because I couldn't, especially when the videos are long, I couldn't fit all of this into one volume, so I had to split the volume into chunks, which was not the most elegant solution. Spatial Functa is another version where we kind of like divide the image into patches to preserve more context of like where in the image that happens. And our approach with the time-resolved component outperformed all of the above. And then what you also looked at is, so the width functor would be like trained per data set. Then on the mixed data set, we lose performance, but as I showed you before, it's not terribly, terribly bad. And this bottom line is the out of distribution performance. So what happens if I train on cardiac and lung and I evaluate on breast? Or for here in this row, I trained on cardiac and breast and evaluated on lung. And this also worked surprisingly well. And then I took this one step further and thought, okay, what happens if I apply my model on data that is definitely never seen before? So I applied my ultrasound model on MRI and also natural images. And what happens was that it can, with these 10 inner loop update steps, it can reconstruct like the overall appearance of the image. So we can kind of tell that it's a horse or it should be a brain MR image. However, what it also does, it introduces ultrasound-specific artifacts. For example, here you see that it introduces speckle noise, which is very ultrasound-specific. And here, especially with the horse, you see the beam of the ultrasound that wasn't there before. And I didn't do much with that, but maybe we can use such an approach for style transfer or something like that. Now, what I was interested in the end was actually the downstream task on this compressed latent space. However, this didn't really work well, or doesn't work well yet, but I show you something that I noticed. So here, for the downstream task on the cardiac data set, the downstream task is ejection fraction. And I see when I apply a transformer, so every video is represented as a sequence of 1D vectors, and I apply the transformer on the sequence of 1D vectors to get to the ejection fraction score. And I see that I get a mean average error of roughly 6, which is, it learns something, but it's not very, very good. Because if I apply a convolutional neural network, such as PocoVitNet, for example, on the original videos, I get a mean average error of 4.3. So I do lose performance from 4 to 6. However, when I then reconstruct my videos, my compressed videos into V-hat, and I apply the same convolutional architecture, I go back to 4, which means that during this compression reconstruction process, I lose a little bit of information, but really not that much, because I still have a mean average error of 4. However, at the moment, I'm not able to extract the downstream score from this compressed latent space, and that's what I'm working on at the moment. It was a very similar thing on the breast ultrasound. However, there my downstream task did not perform too badly. And on the lung is where I struggled the most. But I also think that part of it is that I do lose important information in this compression, because at the moment I lose the high frequency component, and I think especially in this B-line detection, sometimes it's actually needed. Then given these results, I started troubleshooting. So first I thought that maybe when my reconstruction is bad, my downstream task is bad, but then in this plot, I plot the reconstruction performance in terms of structural similarity index on the x-axis, and error in ejection fraction prediction on the y-axis. And you see that these two are not really correlated. So it's not the better I reconstruct, the better my downstream task is. So I don't think I need to focus on the reconstruction at the moment. And the other thing is, like, I started to look at the modulation vectors in this representation space. So here, on the y-axis, I have time. So this is my video over time. And on the x-axis is just the length of my modulation vector phi. That is of length 512. And when I first looked at this, I was like, okay, I'm not surprised that the model doesn't learn that much, because to me it looks very, like, not obvious. However, what you see in this video, you see these like 3 layers. And when you then look at the reconstructed video, or also the input video, is that in this sequence, the heart pumps like 3 times. And this is really like this 1, 2, 3. So there is information stored in there. So that's all stuff that I'm working on at the moment. And so to wrap this up, and just like as a take-home message, this was kind of like a deep rabbit hole. So overall, I presented 2 papers in this presentation. So the first one was the MET-functa that showed an efficient way of representing images, so still images, as a shared neural representation, where we have like this shared MLP and then signal-specific parameters that serve as modulation vectors to this MLP. Then the second part is, how can we extend this to videos? So we had to add this time-resolved component to actually be able to reconstruct ultrasound videos. So that's how far we got. And then, of course, for my specific application in point-of-care ultrasound, what I will need to look at in the future is first the data compression, like how far can we push this? How much can we compress? And this is interesting for storage costs, for example. Then the reconstruction quality could be better. So I will need to explore different activation functions, different loss functions, and so on and so forth. And then, of course, the downstream performance will need to be improved such that we can actually use this framework for diagnostic purposes, also for getting a triage score in the end. That's all but for the presentation, and I think now I'm happy to take any questions. Thank you.
Thank you so much, Julia. And indeed, if you guys have any questions, you can post it in the Q&A section. So far, we have 2 questions. The first one from Ernest. How do you handle spatial and temporal resolution inconsistencies?
You mean when it's not sampled okay, so in the INR framework, I actually don't care about resolution because it's like a continuous function of space. So in this XY, maybe I can show you. So in this very basic functor representation, I have XY, but that's not bound to a grid. So I could also have, so let's say this is 3 and 4. I could also sample 3.1 and 4.1 if I wanted to. So this is not bound to time. In the videos, because at the moment I don't treat it as a 3D volume, I treat it as a sequence of frames. I mean, the only thing that could there be different would be the frame rate, but still, since I fine-tune for every video of my test set, so I optimize all my fees for my test set, this never caused any issue at all.
Okay. Then Sohail asked, in your video version of the INR, now phi1 should correspond to the same time in all the samples, right? In other words, you have to first make sure that all phi1 or phi2 or phi-n frames are synced first across the data set, right?
No, I can start whenever. So it's like in my fees, in my videos, they are not synced. It's just like phi1 is my first frame whenever that first frame starts. But it could be like anywhere in the cardiac cycle. But I do, because when I get a test video, so a video that I haven't seen before, I will learn, I will optimize my fees and my Vs to match this new video. So it kind of like learns to what is the first frame, where am I in the cycle?
That's good. Then a follow-up from Ernest. Have you tested your model on an easier downstream task for which you have perfect baseline? I am testing my pipelines with the easier tasks such as US view identification, and I'm getting good results.
I think I missed the question. What baseline did I?
So I think that the question is like if you have choosing a easier downstream task rather than severity classification.
So the downstream tasks that I showed, so it's quite limited, and this was also like a little bit, it wasn't random, but like these are the 3 downstream tasks that I tackled. So on the cardiac, I picked ejection fraction for the reason that it's really there, the information has to be in the video. Like there's no other way, it can't be anywhere else. So it's really how much does the heart pump. This is kind of, maybe it's too hard. I agree. I never tried on a task that's kind of like baseline easier. On the lung, this is a little bit tricky, but still there is a lot of papers who do it. And this actually, in my opinion, it really lives on the size of the data set. First I had 200, I had terrible scores, then I got to 2000, and by not changing anything, it got way better. And the rest is just also like I just wanted to try something else. But here the results, because the data set is so small, it's maybe not the most representative. I was thinking about applying this model to, a super, not easy, it's just like a very obvious downstream task. I could also switch to natural image, like videos, for example, does someone swim or does someone run or something like this, just to check the method itself rather than being stuck on ultrasound issues.
But perhaps within ultrasound, I don't know, for you do ultrasound in pregnancy, and for example, the task of determining if the baby is in breech position or is correct.
Yeah.
That's kind of like a binary classification. Probably
Yes. Yeah.
is much easier to achieve. I
Yeah.
mean, you
I
have
could definitely try. Yeah.
more complicated things such as calculating the weight of the baby or measuring,
Yeah.
I think, record the spine, because we had to do that with our son. So definitely they also complications because the baby moves. It's not like the lung of the heart is like kind of fixed with the same position, and so you need to figure it out how to handle.
Yeah.
Then Julie, I have another question for these models. Since you focus in the implicit neural representations, do you think it's a much better approach for embedded into the portable device rather than focus on video neural networks, as you mentioned in the first approach, and then do the compression there with some kind of distillation or something else?
You mean so this is really focused then on like once you have it, like how do you get it on the portable device?
Yeah.
That's a good question. I mean, my models are way smaller at the moment than the convolutions. So for a portable device, also when you don't have a lot of money to buy expensive devices, that's useful. However, still need to compress. So what you acquire on your portable device is the video, and then you'd need to fit it to get the phi1 through phi-t, and then you can apply the downstream task. I don't think at the moment that's the bottleneck. I think at the moment really the bottleneck is to get a model to work that is robust enough to use it in the clinic. Yeah, so we are still stuck on that part. Like downstream, it will be cheaper if it works. So
Okay. Then we have more questions. Nina asked, do you have samples? No, do you have to sample your videos beforehand on the same length, or you can use videos at different lengths?
it's just a different length, like any length is fine.
That's good. And what was the spatial and temporal resolution that you use for the videos? Similar questions. Do you have any numbers?
What was the question? A number for what?
What was the spatial and temporal resolution that you use?
Yeah, so the spatial resolution is, so in the cardiac data set, it was given by 112 by 112, so it's quite small, but that's how this data set comes. To make it comparable for all the data sets, I downsampled the lung and the breast to also this size. However, the lungs were like, as per default, how they came, they were way bigger. They were 700 by 700 something. But I wanted to have them at the same size. So that's why the spatial resolution for the whole data set is 112 by 112. Time-wise, it could be anything between. So I discarded everything that was just one frame because then it's basically an image. This happened in the data set. So like I think in the data set I have a lot, like anything between 5 and 300 roughly. And the model can handle all of that. So yeah.
So just to understand that all these data sets don't come from a portable device. It comes from like the typical machine, that the big ones that we have in the hospital.
That depends. So the lung is
Yeah.
portable.
Okay.
That's the one that's collected in Harvard. The heart, that's the Stanford Econet dynamic data set that is not portable. And the breast, to be honest, I don't know. But I would like looking at the videos, I would assume that there's the standard one. And usually the difference between the standard one and the point of care is that there's a drop in quality. And there's papers that show that models that were trained and evaluated on the standard machines, it's just like a drop in performance when you move to the portable device. So there will be like either you have like specialized models that can handle it, but I also think so that this drop is first of all the domain shift between those two sets, and also that the quality is lower in the portable one usually than in the standard one. So you kind of like buy nice to use in the clinic versus the quality, image quality.
Then another question, could you please explain a little bit more about using the sign activation function? What is the reason behind them? And what are the effects of using the sign activation function?
Yeah, so that's a really good question, and I wish I knew. No, I don't do know. So there is a paper that that I showed in the very beginning. This one here at the bottom. So this is periodic activation functions. They were the ones who introduced the sign activation function, and a multi-layer perceptron with a sign activation functions, that's what they refer to as siren, and that's very widely used and very well known by now. And the reason behind this is that in this paper, they compare the sign activation towards the classic ones like ReLU and the other ones. And they say that like the gradient, so kind of like how sharp are the edges, are way better using the sign activation compared to ReLU. However, like this issue of getting a little bit blurry results, this happens a lot also in other papers. So people started to explore what else could we do. And so one other approach would be using a wire, which would be kind of like a Gabor filter instead of a siren. So the siren is really a sine wave.
Mhm.
And then in the Gabor filter, you kind of like cancel out. So you just kind of like take one blip, you add a small blip in the end, and then you cancel it out, which is supposed to help this high frequency reconstruction issue. I read a paper from this year that switched back to ReLU. So I don't think there's like one gold standard answer to this. There has been shown that sign works better than ReLU, but yeah, it's like not very clear. Also, like for this blurriness, there were people who explored, they didn't change the activation function, they changed the loss function actually to get more high frequency or better high frequency reconstructions.
Okay. Then Michael asked, you mentioned compression rate. Do you compare it to classical video compression methods, and how do those compare in compression rate?
Yeah, here I did not. That's to do, I agree. And that's where like on my last point is like the data compression is like marked in red because I will need to explore this more in detail. So for video compression, so one paper that uses Functa for data compression is called Coin++. It's not video-based, it's image-based, where they do something very similar and they really focus on like how much can we compress. The difference from their paper to our paper is that they operate on patches, and we didn't want that because when you then reconstruct patch-wise and you kind of stitch them together, when you look closely, you still see the patch artifacts in the reconstruction, and we didn't want that. So that's one work that uses this framework for compression. For video compression, yeah, I'll need to do it using a completely different framework. I saw one framework who used it, I forgot the name of the paper, but they used low rank adaptation to reconstruct videos. However, they omit this shared part. So they trained one network per video and just did the low rank adaptation from frame to frame. And that's not really what I want, but still maybe we can combine these ideas.
That's good. And Nina asked, how long were the videos? So do you think there is a limit of time for what the INR works? Because the longer the videos, the more information you have to store, right?
Yes, so the longer my video, what happens is the longer my... So for every video, I have one vector v, and if I have 500 frames, I will have 500 vectors v. With my autoregressive sampling scheme here, where is it here? I don't really care how long my video is because I just go batch by batch until it stops. The only thing that can go wrong, and sometimes it did go wrong for long videos, is my video specific representation. I updated only the first 10 frames, for example. And if then my video changes a lot until it reaches the end, for example, if I reach 500, it looks completely different, I may get in trouble. And sometimes I did, but most of the times I didn't really observe much of a drop in performance, because even in my very last batch, so from 495 to 500, let's say, I can still optimize my phi to reconstruct my specific frame. So it's kind of like my phi saves me to some extent, but it's definitely not optimal, my choice of v there. But like in terms of computation power, I don't really care how long my video will get.
That's the answer. And then how long were the videos? I guess for the
Yeah,
depends on the
so
data
that it
set,
could be
right?
like anything between 5 and I think the longest was roughly 300.
300 seconds?
No, not seconds, frames, sorry.
Frames, okay.
Yeah. Yeah, I always calculate in frames, and kind of like the seconds is just like the frame rate times the frames.
Okay.
Mhm.
So I think we don't have any more questions. I leave it here. So thank you so much, Julia, for the nice presentation.
Thank you for having me and for
And
the questions.
I hope to see your work next year at MICCAI when you solve these
Yeah,
little
well,
issues.
let's hope. Okay. Nice.
Perfect. Thank you so much.
Okay,
Bye-bye.
thank you. Bye. Have a good weekend.